Hi, my name is Alexander Howes, and this is my third and final presentation for this class, and this one will be on the Fibonacci sequence. We all know that the Fibonacci sequence is defined by f of n equals f of n minus 1 plus f of n minus 2. It always starts off with 1, 1. Then to get the next index, you add the last two together. So 1 plus 1 is 2. Then you have 2 and 1. 2 plus 1 is 3. Then you have 2 and 3. 2 plus 3 is 5, and so on. I think we all, at this point, know basically what the Fibonacci sequence is, but this project is about its applications and its broader impact. So, occurrences in nature. This is pretty important and a recurring theme that I've found. So, if you make Fibonacci cubes, this image on the left is what you're going to see, or Fibonacci squares. So on the left, you're going to see Fibonacci squares. If you look at the middle kind of bottom, you'll see the white and the purple square are both 1 by 1s. Then you get a 2 by 2 directly above it, a 3 by 3, a 5 by 5, an 8 by 8, a 13 by 13, a 21 by 21. This can continue. What you'll notice about the spiral itself is that it always connects to the corners. Now, if you look at the images on the right, you'll notice that this Fibonacci spiral is actually seen in many different things in nature. For example, the outside of an egg, a flower, even the outer edge of a storm system, and your fingerprint has Fibonacci spirals in it. What do all these things have in common? They have Fibonacci spirals. That's about it. I'll also point out that there are other natural models in computing. Audio recognition and speech processing, that was my first video. Both use natural models. Swarm intelligence, artificial immune system, membrane computing, amorphous computing, homotopy type theory. I'm just reading things off the slide, and I will tell you there are so many if you look them up. Natural models are extremely important because oftentimes nature has come up with a pretty good model for things, specifically mathematically. So, understanding the models that nature has laid before us and then applying those to computing is definitely an art in itself. Moving forward, I'm going to go through 3 applications of the Fibonacci numbers. First, we have the Fibonacci search. This is a log-in search to find any number in a sorted array. It doesn't matter what the length of the array is. This is the basically pseudocode for it. You would let the array be named A, and it has a desired number X. That's what you're searching for. And you let the Fibonacci sequence be defined, in this case, by f of t or f of anything. You basically find the smallest Fibonacci number that is greater than or equal to the total length of the array. And for this purpose, we're going to call that number m. Then we set an index at in the array at the Fibonacci number that is 2 behind the one that we found at m, so f of m minus 2. Then we check, is a greater than the index at that array, or is it less than that? If it's greater than, we call a recursive process. We call this again with a new array that is length index to length of a, and if it's smaller than, we recurse again, but with an array that is size 0 to the index. So what does this do? It means that bigger problems get bigger solutions, because remember those Fibonacci squares that we had? They're continuously getting exponentially bigger. And what this does is it divides our initial array into size n on the left or n on the smaller side, and roughly, really roughly, 2.5 n on the right side. So the larger sets of numbers will get a larger band to operate in. It's a little bit confusing, but basically the Fibonacci numbers are kind of at the heart of recursion. They are a recursive process. So most processes that we have that are recursive can have Fibonacci numbers implemented in them. Next, we have the Fibonacci heap. This is a priority queue operation, and it actually beats out the binomial and the binary heap in overall time complexity. Now, the interesting thing about the Fibonacci heap is that it wasn't designed to be a Fibonacci heap. The Fibonacci numbers were applied to it after the theory was put into practice, because they realized actually last part of that bottom bulletin was what they realized, which is that the size of a subtree rooted in any node of degree k is at least Fibonacci number k plus 2, where obviously f of k is the kth Fibonacci number. So the interesting thing about it is, you know, big theta of log n, which is obviously something we all are striving for when we write code. But this was a idea that then the Fibonacci numbers were applied to, and it made it, and it allowed it to be defined. This is kind of showing that Fibonacci numbers are based in math and nature, like natural math, natural numbers theorem. So whenever you're doing things that you might not have assumed the Fibonacci numbers are applied to, they might end up applying to it simply because they're part of recursive natural numbers theorem. Moving forward, we have Fibonacci cubes, and this is where it gets a bit more complex. Fibonacci cubes are the hypercube graphs, but they always have a Fibonacci number of vertices. So we see that it's 1 and then, or 2, and then if you look at n equals 1, you have 2. N equals 2, you have 3, and then the next one has 5, and then the next one has 8. What they're used for, interconnection topologies, parallel and distributed systems, and finally, more recently, in about 2008, they've been used for chemical graph theory when the blend of chemistry and computer science was starting to hit its height. But why these are different than simply hypercube graphs and why they were originally made for distributed systems is because all Fibonacci cubes, no matter what size, can be defined by the same algorithm to create a Hamiltonian path within it, meaning that no matter how much your cube grows, the same algorithm will produce a Hamiltonian path. And what a Hamiltonian path is simply a path that connects all nodes without hitting a node twice, a traversal through it. What this means for a distributed system is essential, because instead of, if I want to send information to all of the other nodes, either A, storing the shortest path from A to B, or B, calculating the shortest path from A to B, which is obviously the worst thing you could do. Instead, to get information to every other node in the system, all you have to do is apply the algorithm for the Hamiltonian path, move the information from node to node, and dump it off as you go. It's huge, and it makes distributed and parallel systems work. It's the reason that they work realistically, because otherwise the time complexity would get out of control in order to connect when they get bigger. What this also means is that the basis in the Fibonacci numbers and its recursive nature allows quick and effective recovery from any destination back to its origin. Now, getting there in the first place is your Hamiltonian path, and getting back, because they are based in Fibonacci numbers, allows for effective recovery from that destination back to its origin. Now, we've looked at 3 different Fibonacci applications in computer science. But what can we take from this? What's the big picture? When you go into a meeting at a software company, are you going to be able to bring to the table from this presentation? Realistically, it's not either of those 3 applications. What it is the idea that anything based in natural numbers theory is there for a reason. These natural number occurrences are not something that should be taken lightly. And oftentimes a solution to a problem that we come up with in 45 minutes in a meeting is probably not as good as the one that nature has come up with over millions of years. So when we're looking into a problem, the first thing we should ask is this a problem that is in nature? And if it is, how has the natural number theory solved this problem? If we're doing something that's a recursive by nature, should we look at the Fibonacci sequence in order to see if it can help us? And many of these natural number occurrences, many of these relationships can make our code quicker, faster, and easier simply by understanding the natural models that are already existing. Finally, Here are my sources. And that's about it. Thank you so much for watching.